making a remark that the way this one is resolved, although we knew that was in the put into exponent world, therefore it behaves mod q, the way this p mod q pulled out was a lot of crazy calculation in the exponent. So Gauss proceeded and defined something. What was that? Gauss's character sum. Remember the character sum? So he actually approached a little bit further. That quadratic square root, that one. So I'm going to copy that zeta expression over square root. So let me write down like that. Y coming from that half residue set I call A. This one, if you multiply that all out and use the relationship zeta to the q is 1. But you know better than that, right? We also know zeta to the q minus 1 can be reduced, right? But he just uses zeta to the q and rewrite this one in terms of all the lower power, because any higher power will be replaced by zeta to the q. So he rewrote it, zeta to the k, and k going from 1 to 0, 1 to q minus 1, 0 to the q minus 1. This expression we're about to put it here turns out to be the same. What we're about to do today is a little bit more convenient if you put it in the 0 there. Easier to treat. So what was the coefficient of zeta k, if you expand them all out? Anybody remember? So if you multiply this all out and replace every time you have a zeta to the q, replace 1. Then everything is less than zeta to the q, so it's up to q minus 1. If you simplify all that, what was one of the expression? What was the coefficient of zeta k? This is zeta to the first, zeta to the second, right? All that. Anybody remember? This was a Legendre symbol of each of the coefficient. K at mod q. This number picks up 1 and negative 1. Originally, this number lives in mod q world. But 1 and negative 1 is the same interpretation in mod p world. Down there in the coefficient world is mod p, right? This everything is actually taking place over mod p world. So in particular, that's a plus minus 1. If you actually have written down, not knowing the key, you might have discovered, hey, this is always plus and negative 1, and then you might have guessed if there's anything to do with the Legendre symbol of something, then you might discover. Right? That's not how Gauss discovered it. But all we care here is that we're going to prove this one. Why is these two things are equal to each other, right? Not going through how the Gauss discovered. All right, how are we going to prove that? This one, both the square roots of some number, right? So Gauss sum would claim that. Namely, if you raise those guys, the star represents this common quantity or common number in that field extension over Fp. What happened if you square both of them if they're equal to each other? This is the description of this product, right? That's supposed to be this number. If you square it, of course, it becomes negative 1 raised to the Lth power of q. Is that right? Yeah, square root of something, if you square it, of course, it becomes number inside. So all we have to show, we already showed that this one is this. All we have to show is that you square that and show that it's this number, right? If I have two numbers whose square is the same, then is this two number necessarily the same? If I have a number whose square is 5, is this two number necessarily the same? Not really. It could be positive root 5, it could be negative root 5, right? But by looking at the one of the term, you can just flip it. I didn't think really carefully, but it's not that simple, but it's not as difficult as determining whether it's a plus 1 or minus 1, like the law of quadratic reciprocity. So usually when something is not prepared like this, the best way is just put in a homework problem. So we're going to see, we're going to square both of them and going to show that that square is this guy, negative 1 raised to the Lth power q. But is that positive square root or negative square root? Is that exactly the same or they're opposite by the sign? That is yet to be determined, right? Okay, so, but let's first square that. So we're going to prove, almost prove, right? We're going to, for a while, we're not going to touch that coefficient, bk. bk is that k over q. And we're going to work on brute force expansion of the square of this sigma expansion, and then This was a homework problem. You expanding this expression, k going from 0, q minus 1, bk. Treating bk is arbitrary, so you have to carry bk all the time. Z to the k is the expression we have, and we want to show this square is what? Negative 1 raised to the q minus 1 over 2 times q. This is what we want to show, right? And homework problem is it actually squaring this one. And there was like 6 homework ago, there was a degree 3-term homework problem that you actually expanded it and wrote down the product of B0 and B1, all that, and wanted to distinguish what happens. All right, so here is the square. You might have done this in integral part. If you have a square of two things, then if you have a square of an integral, then you can write it as integral times integral. Then you have to change the dummy variable dx to dt something, right? You're integrating 2 times separately and then multiplying is the same thing. In modern algebra and modern analysis, this sum is treated as the same as integral. So technique we developed for this integral is really the same technique in the sigma, right? In many counting world out there, the technique would handle this sigma thing is exactly the same as the techniques in the integral. Integration by parts, substitution rule, all that is kind of exactly the same thing works in here. So we call it discrete calculus. If you look up that term, and you will see. So what I just did is I switched the k to j, right? Same dummy variable, but we have to distinguish the 2 copies of a 2 different thing there, right? Does that make sense? So think about this 2 integral. You know that this is a famous problem, and a problem we calculate is negative x squared dx. Anybody remember this problem from Calc 3? Integrating from negative infinity to positive into negative x squared. The way we prove it is that we actually square this one. Who would have think that is the technique we work, but it was developed like this. And then you write it 2 integrals, right? One for dx, one for dy. And then when we put them together, it becomes a polar integral on the plane, not on the real line. It was originally integral on the real line, but as we swap this to x and y, put them together, it becomes integral on the plane, this Calc 3 problem. From there, you could pass the polar change of coordinates and all that. We could prove that. It's kind of the same thing. So here, k and j are completely independent. You can just swap them inside there like this. K and j is exactly the same indices. They put together in zeta to the kj and bk bj. Is that right? K going from 0 to q minus 1, j going from 0 to q minus 1. There's no point of being lazy in writing here, so I wrote it back. Make sense? Think about the integral swapping around. So you can just put them together. Actually, if you think about this one, there's a lot of distribution law. You have to explain it. But you can play this one with a 3-term by 3-term and see if you believe it. And often it's sufficient for you to believe. Next thing is organizing this one in terms of the powers of zeta to the n, right? So we want to look at maybe 1 plus 3, that's 4, right? Or 2 plus 2, or 4 plus 1. We're going to collect all of them such that zeta to the 4th is always, no matter what the kj is, they all sum up to 4. So you rearrange it, right? So this is a change of variable. Exactly just like in here, we write x plus y, as one variable in there. This is the technique of the substitution. So rearranging it such that n starts from n is going to be that k plus j. So n is going to be k plus j. And k ranges from something to something, and j ranges from something to something, right? Think about all the possibility of k plus j. What do you think the smallest possibility of k plus j is? As k and j independently vary from 0 to q minus 1, 0 to q minus 1. 0, right? 0 is the smallest possibility. What is the largest number it can reach? both of them being largest one, q minus 1, q minus 1, right? So what is it? It's a 2q minus 2. Did I make a mistake in the homework? I think I made a mistake. I thought I put in the 2q minus 1 in there, right? I think I put the 2q minus 1 in. But the largest number we can expect is 2q minus 2, right? Correct? Q minus 1 plus q minus 1. Is that right? That's how it's written. But if you replace that one with a q, then it's still 0, so you can still play with that. But since that Legendre symbol is going to be 0, it doesn't affect it. So it's not really a big deal. You just have to be careful with indices. Now, we collected all the zeta to the end there, and then we collect beta of something index and something index, right? Remember, all these, not the beta, it's a b. B's are coming from, they're originally stuck to the zeta to the k, right? bj was stuck to the zeta to the j power. So when you're multiplying these two things, if you think about it, they're really coming from zeta to the k and the zeta to the j. So the indices there really indicate where that coefficient is coming from. It came from zeta to the k, it came from zeta to the j. If we multiply them together like that, such that they became, as a sum n, these two coefficients, these two indices, as we add them together, it must be n. Exactly that is reflected there. So we're looking at, we're collecting all of them such that k plus j is n. That's all we're collecting, right? So I parameterize the one variable, like k here. So I'm going to focus on the first coefficient. What should be the other one? Such that the sum is always n in that case, right? So it's n minus k. That's the only possibility, right? All right. Make sense? So then you have to think about what is really the condition we have to put it in here. And the earlier exercise with the 3 terms is that is showing you that we better treat it differently. There is no clean formula that goes fill in this part. That's the motivation of the separation of this. Okay? So we separated from that observation of earlier example. In the homework I asked you to separate. Why don't we separate it like this, up to q minus 1 and zeta to the n. And think about what the condition on this thing is, bk and bk n minus k. That was homework. And what was the next one? It's supposed to start at q equals 0, right? N equals q, and go all the way up to where? N equals 2q minus 1. Is that right? 2q minus 2. Move that slightly up. Words. Is that all right? Then here's a zeta to the n. So ended at the q minus 1 and starts in the q and ends at the 2q minus 2. So there it is. So we have bk and bn minus k. Then how do you know where to cut it? It was motivated by that example that if you actually list them down, if you look at example that goes up to second power even, and zeta to the third is replaced by 1, there's a clear difference up to 3 and 3 to 6. There's a difference, so that's maybe there's many other explanation can be. So I'm going to look at first case in here. First case is like this: n is in between 0 and q minus 1. That's the first thing we choose. Then depending on the choice of n, we're thinking about what kind of indices k gives you k and n minus k meaningful. B is coming from 0 to k minus 1 always. The indices of B is always in between 0 and q minus 1. Right, k minus 1. So let's write down k. That itself is index of B, right? So I'm going to write down the second condition. K must be in between 0 and q minus 1. Is that right? So that's natural. But third one is that we have to make sure this n minus k is also in between 0 and q minus 1, right? If it is less than 0 or bigger than q minus 1, there is no such number, or we only have b's that is indices ranging from 0 to q minus 1. So I'm going to put down, all right, n minus k that you see as an indices, and in that expression of both of them, that should in between 0 and q minus 1 as well. Is that right? So I will rather write this one in terms of k so that you can easily compare with n and k nicely. So let's rewrite this one in terms of k. Then I think k goes like this. K, you flip it, and then it goes to the other side. Sorry, I erased everything. Let me go this way. K is here. If you flip the sign so that k becomes a positive, I have negative q minus 1 here. Is that right? And then here's a 0. And then you add both sides n. So it's n. This is something, some simple arithmetic you can do it yourself. I just did it in my head. So that's the inequality, that addition inequality that comes out of the third one, which is the same for the second sum as well. Well, actually, this one's a bit different, so let me rewrite that one later. But if you look at it here, let's think about it. K being less than n is going all the way up to q minus 1. So this looks like an okay condition. Suppose n goes up to, q plus 3. Suppose right end bound here is not q minus 1, but q plus 3. Then here is murky. If n is bigger than q minus 1, k doesn't reach all the way up to q plus 1 or q plus 2, right? This k ends at q minus 1. But since n is going up to q minus 1, this is really sharp bound. The largest number, n, is going to be k minus 1. K can reach all the way up to q minus 1, right? All right, so that's actually good bound there, right-hand side. What about the left-hand side? What do you think about this one? N is smaller than q minus 1. So what kind of number is that? N minus q minus 1. N is actually smaller than the number we're subtracting from n. So don't you think this is a negative number or 0? If n is q minus 1, that's going to be 0. If it is smaller, it will reach a negative 1, right? So this, leaving the negative index here is not a good idea. K only ranges from 0 to q minus 1, right? So would that be good to just go ahead and replace this one 0, 0? Because at worst it reaches 0 and then it goes down to infinity. So isn't this a safe bound? Always makes sense. As long as k ranges from 0 to n, everything is going to make sense. So let's do the second sum. So we can write down in here finally with a different color. Let me use a red one here. If I put k going from 1 through n, no matter what k is, as long as it's 0 to q minus 1, by plugging 1 through n, everything indices here is in between 0 and q minus 1. That's guaranteed by this calculation, right? Any question so far? So this is a simple calculation. So I want you to go and write down this second one, and I want you to do this calculation by yourself, and you can compare this one with mine. So n, it ranges from where to where in this case? From q to q minus 2. Is that right? Q minus 2. How about k? K came from the indices of the first term in that product, the bk and bn minus k. So that still ranges from 0 to q minus 1. Is that right? And n minus has the same condition there. Is that right? And I got this last one here exactly just solving this one without putting any other condition. So you have exactly the same thing, n minus q minus 1, ranging from k through n. Now here, we use actual size of n and all that, right? So therefore, here is the last step. You have to think about the size of n carefully and see if you can come up with a better bound than just not so sharp bound, right? Here, in the left-hand side, was not so good bound, right? So we replace it with a better guaranteed bound. Maybe you can do a similar thing to in here. So I want you to go and think about it. Go. How was it? If you look at the right-hand bound, that's n, right? But n's already greater than q. K is not going to go to q, right? It's going to always stop at q minus 1, don't you think? N is already greater than or equal to q. the largest number that k can reach is a q minus 1. So it'll stop right there no matter what the value of n is, as long as it's that. Left-hand side is that n minus q minus 1, right? N is greater than q minus 1. So, you know, in that n, when the case n equals q, then it's going to start from 1. Definitely not from 0, right? So this number, n minus q minus 1, you know, without the parentheses, n minus q plus 1, it's something greater than, strictly greater than 0, right? So you should put that beginning number right there. All right? Let's go ahead and put that number in there. So what is that? K starts from what number? That number down there, n minus q plus 1. How about the highest number here? That stops at the q minus 1 no matter what n is. So that was one of the examples you did. If you look at the first group, it always, the top limit is changing. In the second group that you earlier homework you did, is that only the bottom range is changing. You always put that 3 in the top range. You had that example before. It grouped in it clearly two different ways. So it becomes like this. From here on, we use the property that z to the q equals 1. So you can kind of knock down this power significantly. And then you rewrite it as if it is 0 to the q minus 1. Now you can put them together finally. All right? Then something interesting happens. All right. So this is a major deal about understanding the limits of all these things. Right? All right. So let's put them together. The third one we're going to do is this the second sum, using this idea zeta to the q is going to be always zeta to the 0, right? Q is going to be treated as 0. So it already starts from the q. So we're going to make a substitution in the second sum. N is going to be m plus q, right? So it starts from q, but if you make this substitution, m is going to start from, let's see, let me write this one like this. Sorry about that. Second sum, we have n ranging from q to where? 2q minus 2, right? And I'm making a substitution, n equals m plus q. So why? Because in that n, we're going to take out the copy of q, right? They're going to be 0. So why don't we take out the copy of q in there? So that's one idea. Let's rewrite n up there as m plus q. Then you know q is going to treat it as a 0, right? So if you plug it in here, what kind of inequality do you get? You see q cancels everywhere. So what is it? It's a 0, right? Going to m up to where? Q minus 2. Is that right? Good. So that's that. So we go and write that the second sum, going from n from q to 2q minus 2. Sorry about that notation. We don't usually write that n up there. So I'm going to go ahead and delete that n. And what is it we have in here? Now z to the n and all that thing. Let me write that down this much. All right, I just copy the second term, knowing that we're working on the second term. So n going through that is the same as m going through 0 to q minus 2. Is that right? N going through these ranges is the same as m going through 0 to q minus 2. So what about next one? And here zeta, n is now replaced by m plus q, right? But you know q is treated as a 0. Therefore, I can just write it as m. Is that right? Then k is just a k. You just have to rewrite it. How about k here? n minus q. You can see n minus q is m. Is that right? So here's n minus q. Originally, there was n minus q there. Where is it? Here is n minus q plus 1. We're about to substitute here m plus q is m plus q is m plus 1. Do you agree? Here, n is m plus q. So if you substitute it in there, that's what you get. Last number is still q minus 1, I think. Right? That's what k value is. There's no n in there. And this one, bk, and n is replaced by what? m plus q minus k. Okay? That's what's being substituted. So let me go back and remind you of what this bm plus q minus k is. Anybody remember what that bk was? bk was a Legendre symbol, right? We're just focusing on rearranging term and just algebraically, not thinking about what the bk is. So this one goes like this. Instead of k, everything goes up m plus q minus k. And what was the modulus here for the Legendre symbol? If you go back to the character sum, that was q down there, right? So it's a q. So how do you treat that q in mod q? 0, right? Isn't that the same as m minus k and q in there, right? That's the same thing. So although it makes no sense if it's indice-wise, but if you use the definition, this one reduces to bkn m minus k, right? Because it's a Legendre symbol, correct? The same value. And miraculously, they're becoming the same right here. bk and bm minus k and bk bn minus k. N is just a dummy variable. Look at it here. It's going exactly through 0 to q minus 2. And if you look at the original one, right next to it, they go through 0 to q minus 2. But we have that, this right-hand side looks exactly like the same from m minus q. K going through m plus 1. That's a little bit different. Yeah, that's a filling in from here to there. So I'm going to write it down. So this is the original expression, right? So here, now finally, original expression goes like this. I'm going to write everything in terms of n. N going from 0 to q minus 1, zeta to the n, k going from 1 through n, bk, bn minus k. That's the first term I just copied. In the second term, I'm going to copy it. The second term is this is new expression. I'm going to write it like a little bit underneath it. But everything in terms of n. That's what I'm going to do. Everything in terms of n. Isn't this m here is just dummy variable, right? So it's going to be everything in terms of n. So here, n going from 0 to q minus 2, zeta to the n, and k going from n plus 1, is that right? Q minus 1. Excuse me. And what is the next one? Here is a bk and bn minus k. For the second term, I change every m to n. Then it became like this. Okay? Any questions so far? All right. Then I'm about to put this one together and noticing, making an observation that this is pretty much the same, except that this is only missing one term there, right? Z to the q minus 1 is missing right there. But it goes all the way to z to the q minus 2. So I can separate that z to the q minus 1 there and then put them together. So let's go ahead and do that. So I'm going to set aside when this one is a z, n is a z to the q minus 1. Because this only goes up to z to the q minus 2, right? So set aside that, just z to the q minus 1. And going from k going from 0 to... Is that from 0? I think I've copied it wrong there. I think I copied this one wrong in here. This is supposed to start from 0, right? Since it starts from 0th power. The bk is a 0. B0, the first, when k is a 0, think about 0 Legendre symbol of q, that we define it as a 0. So this is really a matter, but let's go ahead and fix the indices. And here, that's a 0. And that's a 0. 0 to q minus 1, right? Since I'm plugging in n q minus 1 in here. So that's one term we have. And plus, now this one is going through 0 to q minus 2, right? And the other one is also 0 to q minus 2. So I'd like to claim, I'd like to write it like this. I hope you see now. This one is that because I set aside q minus 1 case, now it's going from 0 to q minus 2. You might have done this type of calculation when you did power series and what is the formula of a geometric series when you do that calc 2. you might have done this type of calculation before. So these are all now zeta to the n there, right? Correct? So I'm going to put this one together. K going from 0 through n, bk and bn minus k, plus this one starts from n plus 1 all the way up to q minus 1, right? And bk and bn minus k. It's interesting how they put together. What do you think? Isn't that exactly the same terms, bk, bn minus k, bk, bn minus k? That goes to 0 through n. The next part starts from n plus 1 to q minus 1, right? So when you put them together, that makes a full 0 to the q minus 1, right? Fine. So here is at 0 to the q minus 1, and k equals 0, q minus 1, bk and bn minus k, and I'm claiming n going from 0 to q minus 2, zeta to the n. What is this power now? 0 going from all the way up to q minus 1 there, right? And this is bk and bn minus k. What is bk there? Now I'm about to, let me just write it down like this, and see which one's better. All right. Realize I forgot to replace that n with the q minus 1 as well. So here's the q minus 1 minus k. That's where I replace those things. I separated that term, that's the part. And q minus 1 minus k. I feel a bit strange that I'm about to realize that I separated the one term, and this became the full term in here with all those n in there. So don't you think this and that part is exactly the same form? So I'm just going to go ahead and claim, and you will easily see that my claim is true. But going from here to that direction, deriving is kind of a little bit confusing. I noticed that these two things are in exactly the same form. Here, inside the sum, exactly the same, where n value is n. Here, that n value is replaced by q minus 1. So I'd like to claim not only this it can be separated like this, because the summation happened nicely like that, you can put it into following form. 0, not just going to q minus 2. If I just go to q minus 1, this formula is still consistent. Zeta to the n, k going from 0 to the q minus 1, bk and bn minus k. So that looks like this one, and I just changed that part q minus 2 to q minus 1. Let's see if this is true. Going through 0 to q minus 2 is appeared all there, right? The last term, q minus 1, if you plug in q minus 1 here, appeared exactly out there. It makes you think about, why did you separate it in the first place if it's exactly like that? What happened is that when we put these two splitted sum together, they put together nicely, then recover the original shape. So if you go through, you will understand the necessity of me separating that q minus first power and putting them back together. Now it became this wonderful sum here. 0 to the q minus 1, and you just sum up 0 to the q minus 1. Although there is still n there, it's really great that we have recovered everything 0 to the q minus 1. Now we're replacing with a Legendre symbol. And then they pulled out this wonderful factorization, which later became something called Jacobi sum. The reason I'm showing this thing, character sum, is that this is the formulation where cubic reciprocity and quartic reciprocity are handled. When you look at the sum and Frobenius action and the way the Legendre symbol is pulled out is a lot nicer and better than the original mu calculation, C1, C2 calculation. So here, with this observation, turns out what happens, these two Legendre symbols multiplied, gave them a clear idea to how to handle other things. So I just replaced the bk and bn minus k there, right? That's all I did. They realized that they can get rid of kind of nicely by pulling out k outside, and it becomes k squared. What do you know about k squared of a Legendre symbol mod q? It's always 1, right? As long as k is not 0. All right, so what they do is that I'm going to go ahead and pull it out like this inside part. Let me just cut it in here. If I factor out k, that you see that the Legendre symbol k there, and n minus 1 in there, right? 1, and then here's a q. And then k is factored out, so what should I multiply next to n? Multiplicative inverse of k modulo q, right? Which is possible whenever k is non-zero mod q. Is that right? That's possible. But k is 0 is allowed here. In that case, you have to give a special treatment. Is that correct? Other than that, it factors out. The next thing they do is that, so this is just 1. You agree? This is just 1. And the next thing they do, this is only for k non-zero, so k is running through what number? K is running through 1, 2, all the way up to q minus 1, right? That's what k is going through. So next thing we're going to do, we have done this type of permutation before. Right now in this sum, k is changing from 1 through q minus 1, right? Relatively n is fixed, correct? So just like we multiply p to half residue set, right? This time we're multiplying n to this whole thing. Let's see, if n is 0, it's not going to be good. So as long as, think about this n times k inverse. What do you think it, as a set is going to be? N is fixed number, and if n is not 0 in this case, if n is not 0, then k inverse is going through all this inverse is the same thing because q is a prime. If you multiply some non-zero number, you know it permutes around, right? So this is exactly the same set as 1 through all the way to q minus 1. Sorry about that. I'm skipping lots of argument here. K is going through 1 through q minus 1. All right? And either you can think of the k inverse or k inverse in Legendre symbol is the same as k Legendre symbol. Because inverses of 1 and negative 1, I mean, negative 1 is the same thing, right? It shouldn't be the thing. But even the k inverse of this thing will give you exactly the same residue set from 1 through q minus 1. If you multiply some fixed number, you know it's going to permute. So everything shows up again. So as a set, that's why it's wonderful about this thing going through q minus 1. N is relatively fixed. Then this thing is this n times n k inverse as a whole through, go through as q minus 1. They all appear as a 1 through q minus 1 again. All right? So I can rewrite it. When n equals 0 is separated, so I have to write it like this, n equals 1, q minus 1. So I'm going to write n equals 0 case later. And k is not 0, so either. So k is going from 1 through the q minus 1, right? And then I factor out those k's because there's non-zero things involved in here. Therefore, that part, k squared part, became 1. So I'm going to write down, I'm going to slide it a little bit so that I can write zeta there, zeta to the n. And what is this one now? It became 1 times Legendre symbol of, right? This k going through 1k minus 1. Let me just use y. Sorry if I keep changing this thing. I'm going to use y. So that n times k inverse just represented by y, right? The y went through all this 1 through q minus 1. Does that make sense? Yeah. Here's minus 1 and Legendre symbol q. That's what happened. Okay? Does that look right? And then it is traditionally they factor out this negative 1. They flip the sign. So that has nothing to do with n or anything. So they pull all the way out. So I forgot to write down n equals 0 case. When n equals 0, when k equals 0, if you look at k equals 0, this becomes 0, right? So replacing with k equals 1 through q minus 1, we don't lose anything. That's the same thing. But when n equals 0, I think you have to be careful. When n equals 0, n is 0, we have all that thing there, right? All that thing. So what is it? K equals 0. So k equals 0 is all right. So it's 1 through q minus 1. So that's a k, q. What about this one? Since n is 0, it's a negative k over q. Is that right? Good. But this one is simply because it's multiplicative k and k negative k squared. So this becomes just a negative 1 Legendre symbol of -1 mod q. Is that right? Because k squared, k is non-zero, what is left is -1. So that's what we have. And they're exactly the same constant. There are q minus 1 of them. That's what we have. All right, let's go back in here. I think probably that's why we want to compare with this -1. So you pull out the negative. So I have pulled out the negative out there. Legendre symbol of -1 mod q. That affects this one. This is flip the sign. That's why I'm pulling out everywhere. So this one in here, and going from 1 through q minus 1. And zeta n and y is going from 1 through q minus 1. And what is this? It's 1 minus y Legendre symbol, right? Plus, let me simplify. This is a constant. There's no k in there, right? How many of the same thing is added up here in the second term? Q minus 1 of them. So I'm going to multiply q minus 1 times -1 over q. All right? Good? So I think it's a matter of showing this one that this one in here is a q actually, actually 1. Then this one add up to q times -1 over q. So that's our goal. All right? But let's think about this part in here. Let me use a different color. Y is going through 1 through all the way up to q minus 1. Is that right? Well, what about this 1 minus y? What do you think this 1 minus? It's shifting, right? Shifting. So what happened if you subtract from this one? If you subtract 1, that's going to be q minus 2. Is that right? No, it's a -1. I'm doing this back. So minus 1, is that 0? Subtract 1, is that -2? -1, that's the right way to write it. All the way up to -q minus 1. Is that right? Then how does it rewrite back? It's starting from, if you start from here, that becomes q minus plus 1. So that's minus q plus 1. That's the same as 1 mod q, right? So I think it's a 0, and that's 1. Go all the way up to, this is supposed to be exactly q minus 1 element in there, right? So I think q minus 2 must be the last number. Is that right? Yeah, I just shifted. Number of elements must be the same. So here's q minus 1 of them. 0's there since we subtracted. There is no 0 in there. Am I calculating this wrong? Is a 1, if you plug in 1. Yeah, this is right. 0 is there. And then except this part, I'm going back in here, doing from in here. So 1 minus. Oh, I'm missing that 1 minus. Is that what you're saying? Yeah, 1 minus is missing. So what is that together? Right, it's a 2 minus q, right? Is that right? Plus plus. What was that one that in before? Why is it so unnatural in here? 1, it's a 0. Let me do it this way. Sorry about this mess. I should have organized better. So we start from 0, and next number is a 2. So it's a -1, right? And -2 go all the way up to negative q minus -q plus 2, something like that. So struggling here. But if you flip this number, this one becomes q minus 1, right? If you flip it. Is that right? Yeah. This one becomes q minus 2. All the way up to this one becomes, if you flip it, becomes positive 2, right? Okay. The only thing that is missing was 1. When you shifted, everything came back except 1 is missing, right? Good. So that's what we know. Let's calculate that guy then. So here is the y equals from q minus 1 of 1 minus y Legendre symbol. we looked at this set 1 minus y there, right? 1 minus y. That was the same as y going from 2 to where? Q minus 1 through just y and q. Isn't that what we just argued it here? Right? The set 1 minus y is the same as 2 to q minus 1. So I rewrote it like this. We have done this type of calculation a lot when we calculate C1 and C2. So I hope it's understandable. Make sense? So let me write it this way then. If I go just to 1 through q minus 1 and Legendre symbol like this has a full set, right? And this is missing 1. So you have to subtract it back, right? Of 1 over q. Isn't that correct? If I write the sum 1 through q minus 1, it has a full set, so I have to subtract where y equals 1. And this one is really easy to calculate, right? Square is a 2 to 1 map, right? Square is a 2 to 1 map, is that right? X squared is a 2 to 1 map. Therefore, half of them is a square and the other half of them is negative square, right? So what do you think about this sum? Go through entire non-zero residues. Half of them is 1, half of them is negative 1, right? So do you believe that's exactly 0? Yeah, half of them get 1, 1, 1, 1. Exactly L of them. The other L of them get exactly negative 1, negative 1. So they cancel. Exactly half of residue and half of non-residue quadratic. Therefore, this is, well, we know about 1 over q, right? Right? That's a negative one, I think. Correct? So what we have proved so far is this value. Let me show you part. We were there, so we have negative 1 residue, right? And we calculated this inside and here is always negative 1. Isn't that what we have calculated here? Always a negative 1. So I have negative 1 in here. And then summation, and this one going through 1 through where? Q minus 1, right? Zeta to the n. Plus Q minus 1 times negative 1 over Q. That's what that is. Agree? I copy the second term. Then inside the calculation there, 1 minus y Legendre symbol sum is just simply negative 1. So I'm going to write that down and probably going to remember what it starts from 1. So the zeta to the first, zeta to the second, go all the way up to where? Zeta to the q minus 1. That's what we are staring at it here, right? Anybody remember about this fact? If I have 1 up there, and who remembers this one? That was a 0, was it not? That was exactly one remaining factor. This one plus that together, if you multiply, it becomes what? 1 minus zeta to the q. That's the geometric series sum, which is very algebraic. If you look at the calculation, it still works in here. What do you know about this one? 0. Zeta has order q, right? So this was the factorization we played with. We know zeta is not 1. Therefore, this was the, I claimed that this is the smallest degree thing, that which I later apologize it's not, but certainly it is in relation we satisfy, right? Therefore, it's a 0. It's a 0. So what do you know about this guy here? If the full sum is 0, what do you know about this guy? Negative 1, right? Yeah, which is just that part is what shows up in it because n starts with 1. If you move this one to the other side, it's a negative 1. Correct? So, where are we? So that's what we wanted to show before. This is negative 1. So I'm going to go back in here and use a different color, the red one here. Finally, we show that there's a Legendre symbol, negative 1 over q. And this whole thing was negative 1, it was here. And then this whole thing became the negative 1 again, right? So altogether it's a positive 1. And plus, there's a q minus 1 Legendre symbol multiplied there, negative 1q. That's just a copy of this thing. So this is a positive 1, and this is a common factor. It's a negative 1 factored out. This is a positive 1 plus q minus 1, right? So what is it? Just a q. So that's It's just a q multiplied by this -1 over q, right? Who remembers the definition of a Legendre symbol? It's a q times that number a raised to what power? Q minus 1 over 2. What is the notation we introduced for Q minus 1 over 2? It's L. It's not difficult, but it's very lengthy, and it doesn't seem like there was just some sort of magic shortcut to do that is calculation. When they lift this one to something called Jacobi sum to handle cubic reciprocity and that, you somewhat go through this business again and again for next higher power. So think about it, we're multiplying 3 times. We just did it 2 times, right? But somebody based on this multiplying it 2 times, we can inductively go to the 3rd power and 4th power. This business that we're multiplying right here, right? -1 raised to L became more and more complicated when you look at 3rd root of Q, 4th root of Q, and 5th root of Q. That's the higher and higher power problem in finite fields, and this guy becomes uglier and uglier and uglier. Not like a need as -1 raised to alpha power. But that's rest of the literature went on for quite a long time to understand 3rd power and 4th power. Those are monomials. So that concludes. What I didn't show that is that a positive-negative business. That remember I was a little bit off by that, but this major deal was done. That's called the Gauss character sum, and some texts just go right into the Gauss character sum to prove law of quadratic reciprocity. Don't deal with this product of 1 minus zeta to the k, that business. So they prefer, this reveals more natural things. All right, that concludes it.